Now let's talk about counting subsets or subgroups. This is also a result from the multiplication rule of counting. So let's start with an example. We want to choose officers and possibly, actually, let's not call it subcommittees, let's just call it committees. Suppose that a new club needs to choose officers, committees, etc., to complete its application to be made an official Cal Poly club. Now, suppose that a president and secretary are to be selected from a group of 6 people. How many choices are possible given the president will be chosen first and the secretary will be chosen second? First question I have for myself is, does order matter? Yes, the president's going to be selected and then the secretary will be selected. Now we know that there's a group of 6 people, and I'm going to make it easy for myself, label these people instead of giving them names. I'm going to call them person A, B, C, D, E, and F. So I've got 6 people. And how many choices are possible given the president will be chosen first and the secretary will be chosen second? So we know that order matters. So let's think about it. Person A could be the president, and then person B could be the secretary. Okay. Also, I like to do it systematically. I think it makes it a lot easier. We know that A could be chosen. Now, can A be chosen? Once A is chosen as the president, can they also be chosen as a secretary? No. So now we could have A and C, A and D, A and E, A and F. Does that take care of every possible combination, every possible arrangement so that A is chosen as a president? And the answer is yes. Well, can we do the same thing with B? Yeah, B could be the president and A could be the secretary. Now let's see. Could B be with B? No, but B could be with C. Hopefully you see that there's a pattern forming. Take a moment, pause the video, and see if you can come up with the rest of the pattern yourself or the rest of this group. So please take a moment and check your answer. This is what it should look like, fully written out. Excuse me. Now, it's fine. We did this, so we wrote it all out. Would we want to do this for anything more complicated than just like 2 options with just 6 people in this case? No, 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 no. So let's think if we could do it numerically. Let's start with one way. We know that we're going to start with a president, and then we're going to get a secretary. At first, we know that there are 6 people available to choose, and then once the president's elected, there are only 5 people left, and we get to 30. Well, are there 30 in here? Let's see, 1, 2, 3, 4, 5, 6 columns and 5 rows. 6 times 5 is 30. So far, it works. Now, it could be a little more complicated than that. So there's actually something called permutations. The number of ordered arrangements, so order matters here, of k items selected from a distinct set of n, a set of n distinct items is n factorial divided by n minus k factorial. This is the number of permutations of n items taken k at a time. Remember, order matters here. Let's see if this would work. What would n and k be here? Well, n is, there's 6 people total, and we want to choose a subset of 2 people. Okay, cool. So I'm going to do that over here using the formula. So we have n factorial over n minus k, so 6 minus 2 factorial, and that gives me 6 factorial over 4 factorial. And you may say, well, what if I don't have a factorial button on my calculator? I don't remember how to use it. That's okay. We could quickly just see we can do 5 times 4, 3, 2, 1, and then 4 times 3 times 2 times 1. You're going to notice all of that cancels, and we're left with 30. So even though we used 3 different methods, did we come up with the same answer each time? And the answer is yes. Now, instead of electing a president and a secretary, let's just suppose that we're selecting a committee of 2 people. Does order matter if you have a committee? No, we're not talking about a chair of committee and then someone else in the committee. We're just talking about 2 committee members. If order doesn't matter, do we think there would be more or fewer possibilities than in part A? Well, let's think about it. If order doesn't matter, would AB be the same thing as BA? Yes, it would. So would we expect there to be more or fewer? Well, fewer. And why is that? Because in this case, AB is the same thing as BA. Now, this is when you may see this. If you've seen combinations before, you'll see this. The number of ways to choose k items from a distinct group of n when order does not matter. So order doesn't matter is n choose k, or n factorial divided by n minus k factorial times k factorial. This is the number of combinations when order does not matter of n items taken k at a time. And you're like, well, the formula looks pretty much identical. They are very close, but here you're also divided by this k factorial. This gets rid of duplicates. So we could go through here and count, get rid of any of the duplicates, and we would come up with the same number, but I'm going to just do it numerically. I know out of 6, I'm going to choose 2. That's going to be 6 factorial over 6 minus 2 factorial times 2 factorial. So then I get 6 times 5 times 4 times 3 times 2 times 1 all over. And I'll just write 4 factorial, 2 factorial there. 4 times 3 times 2 times 1 times 2 times 1. You notice that k factorial ends up being 2, so it's going to cut the number in half. If you want to see, you can cancel those there. The 2 would cancel with the 6, and you're going to end up with 15. So be careful when you're counting these subsets. Does order matter or does order not matter?